Up until now, we've been talking about rigid transformations, or as yesterday's notes section called it, congruence transformations. Rigid transformations maintain the same size and shape. So when we translate, we know we've done it right if the figures look correct. They look the same size and shape. When we rotate, when we reflect, same thing. But today we're talking about something called dilations. And dilations are a transformation in which the figure is enlarged or reduced with respect to a fixed point C called the center of dilation, and a scale factor K, which is a ratio of the lengths of the corresponding sides of the image to its preimage. And that's a mouthful. So all it's saying is that if you want to talk about a dilation, think about what your eye doctor does to your eyes when he wants to see the backs of your eyes. He dilates them, right? He makes the pupil really large, or she. That's a dilation, okay? It's an expansion or a contraction. We're enlarging or we're reducing, okay? How much we enlarge or we reduce is based on something called K, our scale factor. When you have a map and you want to know how far is it between this point and this point on the map, you go to the scale and you see that 1 centimeter equals 1 mile, for example. Okay, that's your scale factor. So it's very similar to what you use in the real world. So when we want to know whether we're enlarging or we're reducing, we're looking for a number that is bigger than 1 if we're enlarging, or a fraction that's between 0 and 1 if we're reducing. Make sense? That's our number K. All right, so the next thing we're talking about then, I want you to focus on this big part of your drawing. The big part of your drawing has 2 triangles. Mine are pink and blue. So when you look at the pink and the blue triangles, which one is the preimage and which one is the image? Pink is the preimage and blue is the image. So is this an expansion? Has it been enlarged or has it been reduced? Reduced. Okay, so this is a reduction. A prime, B prime, C prime is a reduction. So that's your first blank. And we want to know what the scale factor is. It's a reduction. It's reduced. Okay? A prime, B prime, C prime is a reduction. And it's hard to see. Unfortunately, I thought maybe your white colored pencils would draw over the top of that, and it doesn't do a very good job. But it's a reduction of triangle ABC, and we need to figure out what the scale factor is. Actually, they should be the same across all 3 for each point. So the easiest way, The easiest way, we're going to find that out. The easiest way to find it out is to locate either a horizontal or a vertical line in one of your polygons. Do we have a horizontal or vertical line in our segment in our pink polygon? Horizontal. How long is that horizontal segment? That one's 4. Okay. Let's locate the corresponding segment in the other triangle. That one's 2. So if we have a reduction, okay, we reduced it, right? We made it smaller. That means that we want to take the small segment over the large segment. Okay, my small segment is 2. My large segment is 4. So my scale factor is, reduce that ratio. What's 2 divided by 4? 1/2. Okay, 1/2. Make sense? Now, if we don't have a horizontal or a vertical line to deal with, we can use the distance formula on our segments. Okay? So and I've told you over and over and over again that the distance formula keeps coming back in geometry. It does, over and over and over again. Okay? I actually use the distance formula, or use GeoGebra to measure these. And this one, it just halved everything exactly. Because this one was 2.2, and segment C prime B prime is 1.1. And segment AB, if we put that in the distance formula, would be 5.4. Segment A prime B prime is 2.7. Each one's half the distance of the other, half the length. I actually had just measured it in GeoGebra, but we could use the distance formula on these 2 points, and if we did, and worked it out, I don't want to take the time, but if we worked it out, we would end up with 2.2. Yep, 4 boxes. And most of your problems, I think all of them, are going to have a horizontal or a vertical component. So look for that segment and count that one out. Okay? In this case, yes, because we know all the sides. They should all have the same ratio. Okay? They should all have the same ratio. It's that K. K is our scale factor. It's just a variable they chose to use for scale factor. Okay? Other questions on this one? Okay, then the next question I have for you is, I want you to focus on this part of your drawing, which is on the right side. Okay? The right side, we have 2 figures, and we want to know, in the first one, what is the scale factor? Okay? Mm-hmm. All right, so we want to know what's the scale factor. Mm-hmm. All right, so is my blue triangle a image or a pre-image? This one's the image, right? The pink one in my drawing is the pre-image. So did we reduce it or did we enlarge it? We had a pre-image that was smaller, and our image is bigger, so we enlarged it. The extra, these are just showing you the distances between the center of dilation and the lengths between, or the segments between them. They're not necessary. Okay? All right, so we know it's enlarged. So now we have to find a horizontal or a vertical segment because we can count those distances. So Maya, which one do we have, horizontal or vertical? A vertical. How long is the vertical segment on the large triangle? And how long is the vertical segment on the small? All right, so when we have an enlargement, we take the large number divided by the small. So 6 divided by 2 reduces to 3. That's our K. Yes. Mm-hmm. Yep. Absolutely. Great summary. So when we have a big triangle, that's the image, we take the large number divided by the small. And if we have the small triangle, that's the original image, or is the image, we take the small number divided by the large. Okay? Now, here's another example of what they will do. They won't necessarily give it to you on a coordinate plane. Instead, they will give you the distance between the center of dilation and one point, and the distance between the center of dilation and the other point, the pre-image and the image. So in this case, the distance between our center of dilation and our pre-image point is 3. The distance between the center of dilation and the image point is 12. So was this an enlargement or a reduction? Enlargement again. Okay, so one more enlargement. So what do we divide? What by what? Large divided by small. So K is 4. Questions on these? Okay. We're good? Questions on these? All right, so next one. I want you to look back closer to that big image again, okay? And at the bottom of that big image is a statement that tells you that if a point P with coordinates x and y is the preimage of a point, then its image after the dilation centered at the origin 0, 0 with a scale factor of k is a new point P prime, and that P prime is found by taking k times the x value and k times the y value of the coordinate. Okay? So let's see if that held for this particular problem. My point B is 6, 4. What did we say the scale factor for this problem was? 1 over 2. Okay? So if I take the 1 over 2 times the 6 and the 1 over 2 times the 4, what do I get? What's 1/2 of 6? 3. What's 1/2 of 4? 2. So B prime, my new image, should be 3, 2. And it is. Okay? A was 1, 6. So if I take 1/2 of 1, that's 0.5, and 1/2 of 6, that's 3, I should get A prime. And notice we're at 0.53. Okay? All right. So I would like you in the lower left corner to plot triangle RST. Okay? So we're down here plotting triangle RST. Okay. We're plotting triangle RST. Plot triangle RST for me. Make sure you label your points. So when I test you on these, plotting RST, good. When I test you on these, I'll give you 3 points for plotting the points right, but if you don't label them, you lose a point. Okay, so make sure you label your points. So, not quite. Now, listen up, guys. So that's what RST should look like. Okay, everybody have that? Now, our scale factor this time is 3. That means that we're going to make it bigger. We're enlarging it. Okay? So if we're enlarging it, that means that our new R prime will be 3 times the 2 and 3 times the 0. So we take 3 times both of those values, those coordinates. 3 times everything. So R prime is 6 and 0, because 3 times 0 is 0. So you'll plot your new R prime and label it. So we plotted these 3, and that's our small triangle, that's our preimage. And now we're going to multiply. If it was k was 6, we take 6 times everything. But in this case, k was 3, so we took 3 times the 2 and 3 times the 0, and we got 6, 0. So our new R is at 6, 0. That's just R. Okay? It's going to be a big triangle. It's going to be 3 times as large. Same shape, but certainly not the same size. Okay? It's the same shape, but it's not the same size. So when we take the point 2, 2, and we multiply both of those coordinates by 3, we get 6, 6. So the coordinates of S will be 6, 6. So 6, 6 is our new S. So we go 6 over 6 up. That's our S prime. Okay? Now we need to do our T. T was 1, 0. What's its new coordinate going to be? 3, 0. We take 3 times 1 and 3 times 0. Yep. Make sure you label it and connect your points. Questions on this one? We're good? We're just making it bigger. Same size, same shape, but not the same size. This is called a similarity transformation. We're dilating. We're making it larger or smaller. Okay? All right, last example. What happens if our scale factor is a negative 1/4? We multiply everybody by negative 1/4. Okay? So here's where you show me that you know fractions. Okay? L is the point 8, negative 4. So we have to take 8 times negative 1/4, and we have to take negative 4 times negative 1/4. Yep, negative 1/4 times 8. Sorry, thank you. Negative 4, 8. You're right. Okay. So negative 1/4 times a negative 4 gets us what? Natalie, what's negative 1/8 times negative 4? Negative 1/4 times negative 4. Negative times negative is? Let her answer. Negative times negative is a positive. And 1/4 times 4 gets us? Let's multiply the tops. 4 divided by 4 is?
4, 1, 0, 0, 1.
Shh, please. Divide. Divided by 1. Okay? So my new L prime will have 1 for its x coordinate. Dawson, what is negative 1/4 times 8? Negative 1 times 8 is? Negative 2. Okay? So your new L prime is at 1, negative 2. We're making it a lot smaller. Okay? All right, so that's L prime. M was at the point 2, 4. Okay? M was at the point 2, 4. So it's going to be positive or negative 0.5? Good. So negative 0.5 and positive or negative 1? Negative 1. So M prime is negative 5, negative 1. Plot that one. Sorry, negative 0.5. Negative 1/2, negative 1. Okay, so we go left 1/2 and down 1, and this is my M prime. And this one was 1, negative 2, so this is my L prime. It looks like you're doing it wrong, doesn't it? Watch what happens when we finish the last one. My last point was N. N was at negative 2, positive 2, negative 2. What's negative 1/4 times 2, Brooke? What's negative 1/4 times 2? Negative. Okay. Negative 1/4 times 2 is a negative 2/4, which reduces to negative 1/2. And a negative times a negative will be positive, so when we take negative 2 times negative 1/4, we get 1/2. So my N prime is negative 1/2, 1/2. So 1/2 back, 1/2 up, there's N prime. Okay? Connect the dots, and when you're done, it'll look like that. Okay, so what happened? Got a lot smaller, right? Is it in the same orientation it was before? No. Okay. In fact, what happened? Why did that make it, why did it switch it? It, not reflected, but rotated how many degrees? What changes both the signs? 180. It rotated at 180 degrees and made it a lot smaller. Okay? So when you do these problems, when you do these negative, the negative dilations with the negative K, don't be surprised if it rotates it. That's okay. Okay? It's going to rotate at 180 degrees and make it smaller or larger. Okay? All right, I have one last example. It's not on your paper. Okay? I ran out of space. But this last example deals with things like photography. Okay? When I made copies of your handout, this is the same size and shape as my handout, so it's a rigid transformation, a congruence transformation. Same size, same shape. Okay? I took this to the STEM class and asked them to make a poster for me. Okay? Same shape, but certainly not the same size. Okay? I'm not sure what the scale factor is, how big they blew it up. But oftentimes you'll see a picture of something like a spider or a slide under a microscope. And they'll say, hey, the measurement of this particular figure is so many inches. What would it be if it wasn't expanded? Okay? I did. This is a picture of a spider on my dad's farm. It's called a garden spider. That's the same one I showed you before. No, it's the same one. Okay? Shh, no, it was my phone. It's not bad. It didn't move. It didn't move. Okay, so if the spider has been enlarged to 5 times its size, and I measure it on the photo and it's 7.5 inches, and I know that it's 5 times as big as what it's supposed to be, how would I figure out? I divide. We divide by 5, and we get 1.25. That would be the original spider's size. Okay? So you'll see problems like this as well on your assignment. Okay? Speaking of, there's your assignment.